Hello everybody, in this three-part series we'll be looking at the binomial theorem. That is, how do we expand things like this? A binomial has two terms, and we're going to be raising it to various exponents. And while these are fairly straightforward and we can do it fairly reasonably, as we'll see in a second, what happens if we have a plus b to the 12th? Do we really want to write a plus b times a plus b times a plus b times a plus b, all those binomials, and have to start foiling them out? So remember, anything to the 0 power is 1. A plus b to the first would just be a plus b. We've seen that a plus b squared is a squared plus 2ab plus b squared. We could take a plus b cubed and write a plus b times a plus b times a plus b. We could expand it to get this, and we could do the same sort of mess with a plus b to the 4th. We'd list out 4 binomials, FOIL the first 2, FOIL the next 2, then go crazy multiplying them together. For the 12th power, I really don't care to do that. I don't think anybody would care to do that. It would take a long time and be very tedious, and there's got to be a better way. So mathematics a lot of times is all about finding a better way to do something. Are there patterns? Are there shorter ways that we can do this? Are there things that are much more efficient? So let's look for a pattern. Well, 1 could be written as 1 times a to the 0 times b to the 0. Okay, yeah, 1 times something to the 0 times something to the 0, that's 1, you're right, but what's your point? Well, bear with me. A plus b, that could be written like this. So what I'm doing is I'm writing each term involving a and b, which are the things in the binomial. 1 times a to the first, b 0, plus 1 times a to the 0, b to the first. Okay. The next one, I'm also putting coefficients in front of every term, notice. 1 times a squared, b to the 0, plus 2 times a to the first, b to the first, plus 1, a to the 0, b squared. Cool. Try and write down the cubic expansion using coefficients and using a's and b's in every term, so you'll need to add something into the first and last term. So here's what that would look like. And finally, the one with the 4th power would be here. So let's look at some patterns with this. Notice every pair of exponents. They're always adding up to what we had to start with. Every term in this expansion, each one of these chunks separated by the plus, the exponents always add up to 4. In this one, they always add up to 3. 2 and 1 or 1 and 2. 0 and 3, 3 and 0. In this expansion, every term, the exponents will have to add up to 12. Very cool pattern. Now, how do the exponents change? Well, with the 4th power one, starts out a to the 4th, and the next term is a cubed, then a squared, then a to the first, then a to the 0. And it starts out b to the 0, b to the first, b squared, b cubed, b to the 4th. So the first term, the a, the exponent is decreasing, while the b starts out at 0 and increases until it hits the 4. And what about these coefficients? 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. These are special numbers. These are called the binomial coefficients. And we can get them a variety of different ways. One way is that they come from Pascal's triangle. Notice that 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. These terms here, these numbers here, are all the red numbers from this slide right here. And they're arranged in a triangle for a reason. There's a nice pattern as to where these numbers come from. We can generate this triangle. It does go on forever. But starting with this row here, this would be considered row 0. That was the coefficient of the exponent 0. This would be row 1. Then row 2, starting after row 1. Notice 1 plus 1 is 2. 1 plus 2 is 3. And same, 2 plus 1 is 3. Anywhere in here, 1 plus 6 is 7. 6 plus 15 is 21. 70 plus 56 is 126. We could continue this. This spot right down here would be 330, because 120 plus 210 is 330. We could generate this next row. Every row begins and ends with a 1. And beyond that, we take the two numbers above it, add them together, that gets us the next one. 55. 165. And another thing to note, another thing worth noting, is that if I draw a line down the middle of this triangle, it's symmetric. The numbers are the same on both sides. Okay, cool. Well, you know, I really don't want to draw this triangle every single time. These numbers can also be calculated in the calculator. They can be found using an operation called combinations, and we'll get into this more later. But in this row, 3, 0, 3, 1, 3, 2, and 3, 3. This is read 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3. The way we calculate these numbers, in the calculator, we'll jump to the calculator page, we go menu, then we'll go to probability. This calculation is used a lot in probabilities also. And we're going to go down to combinations. And now it says NCR, you're going to put the row number, the big exponent, the main exponent from the problem, comma, whichever one we're using. 3, choose 0 would be for the first term. It's 1. I can change this to 3, choose 1. I get 3. 3, choose 2 is 3. And 3, choose 3 is 1. 1, 3, 3, 1. So I'm generating these terms from the calculator instead. So, in general, we can say the coefficient of the term containing a to the n minus r times b to the r in this expansion is n choose r. So if we can identify the exponents on the two pieces in that term, we can know which binomial coefficient to calculate. So here we go. We're dealing with x plus y to the 8th power. I want x to the 5th. Y cubed. In this problem, n would be 8. If we're looking at Pascal's triangle, we'd be looking at row 8. So what's r? Well, r is going to be the coefficient of the second thing in these parentheses. So it's going to be 3. I'm going to be calculating 8, 3. Another way to figure this out would be to list some terms. We're going to have a whole bunch of things added together. I need to find the one that's going to have x to the 5th y cubed. Well, this first term is going to have x to the 8th y to the 0. Remember from that very first slide, it starts out x to the 8th, this first thing to the 8th power, the second thing to the 0. And then the first exponent decreases x to the 7th and y to the 1st. X to the 6th, y squared, x to the 5th, y cubed. And this first term would be 8 choose 0. This would be 8, 1. 8 choose 2, 8 choose 3. If I'm going to go to Pascal's triangle, I can go to the 8th row. This is 0, 1, 2, 3. I bet it's 56. Let's go to the calculator and double check. So I want combinations 8, 3. 56, there we go, same number as in my triangle, that's amazing. That really, it's pretty cool there. Second example, find the y cubed term. Notice this one doesn't ask for a coefficient, it asks for the entire term. So I'm going to give an answer that's more than just 56 like here. I'm going to actually give the term involving the y. So I'm going to think about my expansion. I really like to put some blanks on my paper like this. This first term is going to have 2 to the 5th, y to the 0. Then 2 to the 4th, y to the 1st. Remember, these exponents always have to add up to 5. And the first exponent decreases, second one increases. 2 squared, y to the 3rd. There's my term that has y cubed. Now what's the coefficient going to be? This is going to be 5, 0, 5, 1, 5, 2, and 5, choose 3. So this is what I need to evaluate. It's going to be whatever 5, choose 3 is. Let's calculate that quick. $10 times 2 squared, which is 4, times y cubed. So 40y cubed is that term more than just the coefficient. If you can sort through these terms, if you can count, you really can work through these binomial expansions. That, ladies and gentlemen, is all for today.